Okay, so we won't get to an assignment slide, so that's good. I just want to do a few slides here, okay? But you might want to bring your calculators Monday, so I think we're getting close to the whole calculator bit. Okay, so one thing about science is it's, I want to say universal, but at least it's global. So the scientists here in North America need to be able to talk to the scientists in China, not to mention commerce. Oh, forget that. I mean, don't forget that, okay? So when we say a pound is a pound, it needs to be a pound. So of course, pound, we're measuring mass, and we need to be able to go back to some sort of reference standard, okay? So these are just kind of general. So are these where you have a few blanks to fill in?
Yes.
Okay, yeah. So you have a few blanks to fill in, guys. And if I go too fast, let me know. Okay, mass in general, you're measuring the amount of stuff there is in your object of interest. Actually, to me, mass, you're kind of measuring the amount of atoms there are. Length is the distance between 2 points. 2 dimensions. Volume kicks it up to 3 dimensions. Okay, volume is how much space something occupies. Temperature, we'll talk more about this, but if this is my thermometer, what temperature is actually measuring is, what's this? Yeah, kinetic. Yeah, the motion of that matter, exactly. That's what your thermometer is measuring, okay? So that's what the temperature is. Now, what this is telling you, and you guys, I think, got this. What if I have 2 chambers. This is chamber A, and this is chamber B. Chamber A is hot, chamber B is cold. What if I open a door between their chambers? This is hot, it's going really fast. This is going slow, the gas particles in the chamber. What's going to happen?
They'll mix and it'll equalize.
They'll mix and equalize,
A little bit
exactly.
of high.
This hot one will go over here. So what this is saying is what direction does heat flow? And heat will flow that way. So temperature tells us that. Okay, so how do we get our standards? I think we should take a road trip to, to Paris, France. And there is a little chunk of metal that is actually exactly 1 kilogram. And everything, then what they do is they take that piece of metal and they make baby standards, okay? And then those baby standards make other standards, okay? And then they go out to the world and everybody can use them on their scales. Isn't that cool? But they have like a pedigree. Like when you buy a standard weight, it like tells you like where it's trackable. So I think that's neat.
Some guy was like, that's the piece of metal we're judging everything off of. Like one day he was like, that's it.
That's it, yep.
Well, why did he decide on metal?
Good point. Well, you know the French. They're so
Yeah.
bossy. So I don't know. Scientists got together. Yeah. But that little chunk of metal has been in the news because this maybe been a year and a half ago, but it was like it lost some weight. It's like, guarded, and anyway, I'm sure it's like a natural, probably just a natural decay, radioactive decay. Awkward. So length is distance between 2 points.
So what do they do?
What do they do?
Is there some type of repair process?
Add a little bit back. I think what they do is take it into consideration then when they make a new generation of standards from it. So it's not exactly 1 kilogram anymore. So then the new standards they take to go out into the world have to be...
Or they just make a new one?
I don't know.
I mean, from a standard that they'd already created from the original.
Yeah, they might. I don't know.
Before it's so far gone.
We'll have to look into that.
Something with a longer half-life, so.
Yeah, they won't run into that problem for...
Maybe a whole day.
It's interesting. Okay, so length, now this is not, I've never seen this traceable, because, we have yardsticks around here, a yardstick, or, if you have a tape measure, how do they know an inch is an inch? And it actually can go back to the speed of light, which light is really fast. And I don't know, I can't even picture how they do this, but there's some standard way. Okay. And then volume would be standard based upon length. Time is standard, again, or in kind of a way that I can't relate. The oscillation of a cesium isotope 133 spectral line. Temperature we can relate to, I think. Okay, so water, and this is, how do I say this? Some of you may have run into this before. Let's see. Triple point of water. Okay, so if this, oh, it's pretty dark. Let's see, this is, I'll put P for pressure. Okay, and this is going to be my temperature. And if I make this a diagram for the substance water, it kind of looks like it's got a, okay, so this is my solid, this is my liquid, and this must be my gas. And it kind of makes sense because as you increase temperature, you're going to get gas. Okay, and actually as you lower the pressure, you're going to get gas. As you cool something down, you're more likely to get solid. Actually, as you increase the pressure, you're more likely to get solid. So we have these three sectors. And it's unique for each substance. This is for water, okay? But anyway, that is the triple point of water. Isn't that cool? What does that mean? It means at that pressure and at that temperature, it exists as all three phases. Isn't that cool? So that's the triple point. Okay.
Does it affirmatively exist in all three phases, like some sort of super phase, or
As
does it depend on what phase it was before it reached the triple point?
As far as I know, it's kind of existing as kind of a slushy, gassy, liquidy, solidy thing, you know?
Okay.
Yeah, it's pretty cool. I guess I should have, if I'm doing this right, we have an abrupt end to, I think this one has an abrupt end, and this one goes on. Does anybody recognize 273.15? Have you run into that before? I'll remind you, and we'll talk about this later. If it's a number that's like, I know that number.
It's the Celsius to Kelvin conversion.
It is the Celsius to Kelvin conversion. So if you have, let's see, how does this work? If you have degrees Celsius and you want to get to Kelvin, you add 273.15, and that will get you to your Kelvin temperature. So 0 Celsius is what Kelvin? 273.15, yeah. Okay, cool. I was going to say, well, what's absolute zero? What if this is 0? Okay, then what is the Celsius temperature?
Negative 273.
It is negative 273.15. Good. If you didn't follow that, that's fine, but good job. Absolute zero is the temperature that this stops. I just think that is so cool. You know, I go kinetic energy and it just stops. Oh my gosh. Okay. All right. Amount. Oh, the mole. Oh, everybody loves the mole.
Do you celebrate Mole Day?
We do. October 23rd?
Starts at 6:22 a.m.
Oh, okay. At 6:22 a.m. on October 23rd. So what is the, do you guys remember what's the value for a mole? 1 mole is equal to? That's the one I use. Then I go times 10 to the 23rd. And Christian was reminding us we all need to mark our calendars because if you take the date, what's the date 10/23? October 23rd.
I was like, is that a trick question?
So October 23rd, and I didn't realize this is at 6:22 a.m.?
This is when it starts, yeah.
Okay.
That's, may have just been something that,
But
My chemistry
6:22
teacher
a.m.
told me to-
it begins. Begins a day of celebration of the mole. Yeah, we should celebrate.
How do people celebrate that?
Strangely. I don't know. What day of the week is that on? Does anybody know?
no.
They're looking it up.
October 23rd, it's a Sunday.
We'll have to think about it. Very good. Okay. So, do you see some gradations on glassware there? Different gradations on the glassware. That's just the marks. Okay. We're gonna kind of ramp up, and Monday we're gonna talk a little bit about accuracy. So, accuracy is how on the nose it is. So, what do you think accuracy lies? If I look at the gradations here on this beaker, I go up to 100 mils, but I also go up to 100 mils in this graduated cylinder, okay? Which one seems probably more accurate?
The graduate stuff,
Yeah,
there's more little tick marks.
graduated cylinders, more tick marks, yeah. So this is more accurate. So 100 mils is different, and we'll talk kind of about that. We call it uncertainty, and again, we're gonna hit this on Monday. Uncertainty is kind of the wiggle in the, what it is. Every time you measure anything, whether it's volume like this, or whether it's time, or whether it's distance, there's like, there's uncertainty. A lot of times we just say it's plus or minus. Sometimes we'll call it a tolerance. But anyway, I want to talk a little bit about abbreviations for some measuring things. SI stands for International Standard Units of Measure. So for length, it's the meter. For mass, it's not the gram, it's the kilogram. For time, it's the second. For temperature, it's Kelvin. For amount, it's mole. I think that is so cute, the abbreviation. You get to drop the E from mole. I guess it's 25% less, right? For electric current, it's the ampere, and for luminosity, it's the candle. Okay, so I'm going to highlight 4 prefixes, metric prefixes, that you need to know what they are, even though there's more metric in it on a test. Not to say that you would not have, where's my arrows? Not to say that you wouldn't, for homework, need to know what these are. It's not advancing. Come on. Oh. There. Oops. There we go. Okay, so the arrows, I guess there's 5, not 4, I lied. But you need to have a sense of what the kilo prefix means. And actually, of the ones you need to commit to memory, kilo is the largest. Kilo means 1,000 times whatever that base unit is. So if you have 1 kilometer, how many meters do you have? Yes, 1,000 meters, perfect. So 1 km is equal to 1,000 meters. The prefix kilo means 1,000 times. You also need to know centi. Centi is 1/100th of. Okay, let's say you have 1 centimeter. How much of a meter do you have? 0.001. Very good. Or 1/100th of a meter, same thing. Perfect. But we definitely go with this instead of this. It's easier. Milli is 1/1000th. So I think you get the idea. Milli is 1/1000th. I also want you to know micro is 1/1,000,000th. And nano, I don't do as much with that, is 1/1,000,000th. So know those. So you guys told me 1 centimeter is 0.01 meters. So what I usually do is instead of saying, to use this as an example, instead of saying this, if I multiply both sides by 100, I can do that, right? Because I'm going to multiply both sides by 100. Okay, and the reason I'm doing that is to get rid of my decimal. So 100 times 0.01 is 1. And 100 times 1 is 100. So a lot of times, I mean, these are the same thing. They're totally the same thing. If you're like me, I'll put it this way. You're in good company. I'm not saying you should do this, but you're in good company if you put 1 meter is equal to 1,000 kilometers. I know it's wrong, and it hurts our eyes, but it's easy to, you just concentrate when you're working with metric stuff, okay? Because that's not right, right?
Right.
Okay. But, so just, right? Okay. Okay. What?
That'll end up confusing me if I read it.
Okay, don't do that. Don't write it down. I didn't say that. Sometimes, so you need to memorize those. I guess I added, what did I add? Pico. Okay, so off the Pico sauce. So I added Pico, so you need to memorize those 5 metric prefixes. You also need to memorize that first equivalency statement. I call it an equivalency statement because I'm simply have 2 quantities with an equal sign between them. Okay?
I
So-
only had 4. The kilo, centi, micro, pico. These
And
just-
centi?
Got that one. Do you want the deci?
I wonder what let me see.
There's kilo, centi, milli, micro, nano.
Oh, nano. Yeah, I
missed
didn't
milli.
have pico.
I think I missed
Yeah.
Just making sure.
Yeah, it wasn't pico, it was nano. Nano's kind of nice because like in light and wavelengths, sometimes they'll go nanometers, so. Cool. Good job. Okay, so know this equality and notice, and we'll talk more about this on Monday, but it's kind of fun because the metric system, which is meters, okay, kind of shook hands with the English system, which is inches, and then by definition, we have this cool relationship that 1 inch is exactly equal to 2.54 centimeters. Okay, so you don't have to memorize the other 2, okay? But they are other great equivalency statements that we can use in our problems. Okay, and then memorize this one too. So 1 centimeter cubed means that you, if I had a ruler in here, I could show you, but you have a box that's 1 centimeter by 1 centimeter by 1 centimeter. Oops, boy, that's not a very good box. Something like that. 1 centimeter on all dimensions. And then the volume it contains is 1 cubic centimeter. In nursing, or in medical fields, what do we call this?
CC.
1 cc, yep.
Actually, getting away from cc's.
Are they? What are they using, milliliters instead? Okay.
They're almost going solely, the older nurses will still use cc's, but all their new ones, they're training to do away with cc's.
That's interesting. Was there a reason for that? Just to...
I'm sure I was told, but I don't remember what it was.
That's interesting. So know that relationship. Okay. And kind of the last slide I wanted to get to is this one.
Actually, I think it has to do with the, all of the abbreviations for things, and it's misunderstood for other things. Like it's
Okay.
easy in paperwork to get confused, so I think
And
it
one
just has to
thing-
do with something simple like that.
That makes sense, because one thing you don't want to be confused in is,
Yes.
yes. Well, that's cool. I'm glad to hear that. So it's case sensitive too. Oh, I guess I did want to do this slide too. So let's do slide. Okay, so actually there are a couple things here. So we're tempted, and sometimes you'll even see me as I'm working, you don't put a period after your abbreviation, so Graham is just the letter G, and Graham is not GM, okay, just Graham, with no period. And then we don't use an S. So, meters is just M. Any questions about all that? Cool, that's perfect. So we'll pick up here on Monday.